Inverse functions undo each other. For example, if f of x and g of x are inverses of each other, then whatever f does to a number, g will undo that to take us back to the original number. For example, let's evaluate f of x for the value of 2 to get a result of 5. Let's then plug that 5 in the g function, and it takes us back to the original number 2. If we have a function that's 1-to-1, which means every x value has only one y value and every y value has only one x value, then we should be able to determine the inverse of the function that will make this undoing possible. A simple example of where this could be useful would be if I'm taking letters of the alphabet and numbering them 1 through 26, and then using the f function to add 3 to every letter. So a, which is 1, becomes 4. If I send you that message and you know that the inverse function is the g function, then you can take that 4, subtract 3, and it takes you back to the 1, which is the letter a. So as long as we have a 1-to-1 function where each of my numbers gives me one number coming out and each of your numbers that you put in gives you one number coming out, then, and if they are inverses, then you can take my coded message and decipher it back to my original message. Now we can find an inverse of a function if we don't know what it is. If we start with a 1-to-1 function, let's start with this function. We can find the inverse of that function by following this process. I'm going to call f of x y, and I'm going to interchange the x and the y variables. So I have x equals 2y minus 1. And I want to solve for y. So I'll add 1 to both sides and divide both sides by 2. I'll call this my inverse function. Since I started with f of x, I'll call this f inverse of x with little, it looks like an exponent of -1, but it stands for the inverse function of the function f. So I have my function and the inverse of the function. So if I put a number in f of x and get a resulting number out, I can put that resulting number in the inverse function and come back to the original number that I started with. Well, this helps us to determine a way of verifying that we actually have inverses. That verification comes through the composition of functions. If I perform the composition of f of f inverse and I end up with x as a result, then that means that I put a number in the inverse, the resulting number went into the function itself, and it came back out as x. That means that they're inverses. As well as proving it the other way, if I have f of x inside the inverse function, if this results as x, then I verify that we actually have inverses. Well, let's do the first composition. F of the inverse was x plus 1 over 2. The f function was 2 times x minus 1. I'll put x plus 1 over 2 where the x was. If I simplify this, the 2's will cancel. I'm left with x plus 1 minus 1, which is x. So I started with x, and I ended up with x. If I do the composition f inverse of f of x, f inverse of f of x, which was 2x minus 1, the inverse function is x plus 1 all over 2. I'll put the 2x minus 1 in where the x was in the inverse function. If I get rid of parentheses and simplify, I also get x. We started with x, we finished with x. So we had a process of finding the inverse and a process of verifying it. We also have a process of looking at the inverses graphically. Here I have my original function f of x, which was 2x minus 1. Here I have my inverse function, which is x plus 1 all over 2. And here I have the line y equals x, the line that goes through 0, 0, 1, 1, 2, 2, and so on. The graph of a function will reflect across the line y equals x to get the inverse. And you might be able to see that f of x reflects across the line y equals x to give us f inverse of x. Let's look at another example. The function is the cube root of x minus 4. It's a one-to-one function. Every x value will give me one y value. Every y value comes from one x value. What I'd like you to try to do is to try to come up with the inverse of this function. Try to verify it using the composition of functions both ways. And then if you have a graphing calculator, try to graph the function, the inverse, and the line y equals x, and see if it looks like the function and the inverse reflect across the line y equals x. Pause the video, try to do that, come back and check your answer. To find the inverse of the function, I'll replace f of x with y. And interchange my variables. I want to solve for y, so the first thing I can do is cube both sides, which will get rid of the cube root on the right hand side and cube the x on the left hand side. And then I'll add 4 to solve for y. So I think the inverse is x cubed plus 4. If I want to verify that, I can take the composition f of f inverse of x, also take f inverse of f of x, and see if they both result in x. F of f inverse, the inverse function being x cubed plus 4. I want to put that in the original function, so I have the cube root of x minus 4. For the x, I'll replace it with x cubed plus 4. If I get rid of the brackets, I have x cubed plus 4 minus 4, which is the cube root of x cubed, which is x. If I take f inverse of f of x is the cube root of x minus 4. Then I can take the inverse function, which is something cubed plus 4, and I can replace that x with the cube root of x minus 4. If I cube the cube root, I'm left with x minus 4 plus the outside 4, which results in x. So we found the inverse, we verified it. Let's look at it graphically. Here we have the function f of x equals the cube of x minus 4. Here we have the inverse function, f inverse of x equals x cubed plus 4. Here we have the line y equals x, and you may be able to see that the function reflects across the line y equals x to give the inverse function. So basically in this lesson we looked at three main ideas of inverses. We looked at finding the inverse, verifying the inverse with composition, and what inverses look like graphically.